And yeah, so we do have a lot to get through today just to cover basically the most essential details from the last half of the class. So we'll fly through some of this. If you have any questions, just get my attention. Otherwise, I'll probably just carry on quickly to get through it all. Just like the midterm, this has seemed to become the tradition in CS24 is that it's a 6-hour exam, multiple sittings. I don't want you to have to sit anywhere for 6 hours. Especially because 6 hours is a long time. So you want to take a break, you want to go for a run, take a nap, whatever, that's totally fine. The basic rule is that if you're thinking about the exam, the timer should be running. And so that kind of excludes tactics like, I'm going to read the exam and then go study the stuff that I saw in the exam, but I'm not technically thinking about the exam so that I don't have to run the clock. That's kind of naughty, and so don't do that. Anyway, enough about that. The other things, like I say, are open anything, any course material, including solutions, your graded assignments, and so forth. You can use your computer, but generally the final exam doesn't have that much implementation because we've gotten to the point where the systems are so complex that it's really difficult to actually be able to implement anything at this point. So there might be a little bit of coding here and there, but there generally won't be like massive, substantial coding. So thankfully that part is not really an issue. Yeah, it's a lot of conceptual stuff. I think I've talked about this a little bit in a sec. As far as internet usage is concerned, I apologize for having to be so detailed in specifying this. I mean, I'd love to just say you can access anything that is cited or linked from the CS24 material. That's pretty fine as far as figuring things out. Like I say here, Moodle website, referenced by the Moodle website, anything referenced by the final exam, or any other CS24 material, really. But you obviously can't search for things that give you answers, and you can't ask people stuff on the internet. And why do we say this? Because people have done these things. And it's always frustrating because it's like no collab kind of should make it really clear that that's not really allowed. Yes, question?
Can we use the Oracle and documentation?
Yeah, is Oracle's, I keep hearing this from year to year. Is the Oracle's IA32 documentation better?
I don't know. What do you think?
Okay. Is it like just different, so it's kind of helpful sometimes and not helpful other times? Because I can just, in the future, just put a link to its documentation online. But yeah, that's totally fine. If it's just IA32 documentation, like if you want to refer to Glenn George's cheat sheets, I know he has some for 5X and blah, 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 whatever is totally fine. Just, if it gives you answers, don't look at it. That's kind of like, oh, whatever. Do you really need to know any IA32 for this exam? I don't think you do. I mean, you have to know the architecture of the system, right? You have to know memory stuff, but you don't really have to know instructions. So, but whatever. If you want to read it for funsies while you're taking your exam, that's totally cool too. Any other questions? Alrighty. So, yeah, basically anything covered in the last half of class up until today is perfectly valid fodder for the exam. And so these are the kind of things. I usually like to pull problems from all of these general areas. So memory hierarchy, hardware caches, there's almost always a caching problem. And this year is certainly no different. Locality, we'll go through some of these things. And just be really sure you understand the different kinds of locality. Because if you're like, this is spatial locality, and this is temporal locality, and you happen to be right, the TAs will be like, yay, they understand, and you'll get points. So that's the awesome way to do it. Also, if you understand things like, make sure you understand terms like direct map, N-way, or we say E-way, set associative caches, fully associative caches. If you understand all of these terms well, you should have no problem. So that would be the kind of thing that I would review before this exam. Let's see, processes. So almost always, again, scheduling. I try to have some kind of scheduling problem on the exam. I often have some kind of locking problem on the exam, and they're not like, here's a program with 45 locks and it deadlocks a third of the time when you run it. Try to figure out why. That would be really rude. I've had those kinds of bugs. I've had bugs that have lasted a month because I couldn't find that kind of stuff. So why would I do that to you? Anyway, so there'll be some basic problems like that. And typically, sometimes there's signal stuff. Not always. So I'll leave that up to your imagination there. And then virtual memory, again, almost always makes an appearance because it's a really, really important topic in computer systems. Let's see, yeah, and if anything is touched on from the first half of the class, it will be in more of a cursory overview type thing. So again, be familiar with the general concepts, but you certainly aren't expected to have like an intimate knowledge of different kinds of allocators. We don't really do that as much in the last half. Okay? All right. So yes, you're free to forget a lot of that information now. Okay, yeah, so it tends to be conceptual in nature. I've already talked about this. So basically, I give you, here's a system. Tell me some general characteristics about it, or here's these questions. Tell me some answers for these questions. So, like I said, if you're really familiar with the concepts, you'll have no problem with these kinds of questions. Also, things like, are context switches free? The answer is obviously no. So make sure you understand those kinds of things, because typically those inform our knowledge or analysis of these kinds of systems. Is it cheap to trap into the kernel? No, not really. It's definitely cheaper than a context switch, but context switches often occur at those points. So you have all kinds of things like that you should basically have a good sense of in your mind. Okay? Page faults are bad. Cache misses are bad. Those are the kinds of things you should think about. Okay, another thing that I should mention also, just, especially since we're starting to talk about caching and computer memories and things. I mean, the size of caches really has an effect on how we design our systems, because if I can design my algorithm to work with chunks of data that are the size of one of my caches, then that's really good for me, because now I can know that I'm going to be leveraging that cache. Even if I have poor locality, if I can divide the data up into chunks that will fit into one of my caches, then that's actually not too bad. So anyway, that's just an aside. Yeah, so these were the basic principles, the physical principles that we discussed. Small memories are faster than large memories. If you hold the technology constant, this is basically always true because of physics. But then we also have multiple technologies, and we can make large, dense memories that are cheaper per megabyte or whatever unit of storage you want to use. And you can make them more cheaply. And because they're denser, you tend to have more complication in retrieving data. Think about spinning magnetic platter covered with rust. I've got this arm that I have to swing and so forth. That makes it more expensive to retrieve that data. Also, this makes us sad, the processor memory performance gap. Okay? They're both increasing in speed, but one is increasing faster than the other. So we have a gap opening up between our processors and memories, and so that obviously motivates this approach of caching. Okay? We talked a lot about this stuff. The fundamental idea is when I retrieve a value, the processor, or I should say the processor's caches, fetch multiple values surrounding it, so we fetch a whole block of data. And so we have this assumption that the program is going to exhibit some kind of locality. This is what we mean when we say it's going to probably access the same value again soon. That's temporal locality. And likely to access nearby values soon. That's spatial locality. Okay, so so this is what I just talked about. Make sure you understand the difference between these terms. Spatial is it's nearby, and temporal is the same thing soon. Okay, let's see. This is all kind of really obvious stuff. But yeah, I mean, it's kind of really interesting. If you can design an algorithm that generates very few cache misses, you do start to get the size of the large memory at the speed of the smaller memory, which is pretty amazing. Okay, this was the memory hierarchy. And of course, each level is providing caching for the level below it. And you can see some of them, like L0, we figure out at compile time because it's too complicated to figure out at runtime. And actually, even that is not entirely true anymore because of things like register renaming and out-of-order execution. The processor is actually getting to the point where it can figure out that stuff, which is pretty awesome. And then L1, L2, and L3 are the ones that are our hardware caches. They tend to have anywhere from 3 to 25 clocks for hits, and so obviously we don't have a lot of time, so we have to hard code certain things. Hopefully you remember that. Placement policies, replacement policies. L4 to L5, we have a lot of time in between those, so we have larger block size, and we have much more clever replacement policies for those kinds of things. And then L5 to L6 we don't really talk about, but you can use your imagination. It's the same ideas again. It was kind of funny because I was reading the homework 8 feedback, which is all very helpful so far. It's given me ideas for next year's homework 8. And somebody was like, well, this is like the caching lab all over again. And I'm like, yes, it is. That's exactly what it is, because that's what we're doing when it comes to main memory and local storage. That's just the way that it is. Okay, except that we get to be a little bit more clever in our replacement policies. Okay, now, yeah, like I said, in these lectures we have multiple levels of caching, and we often have shared caches now, so we have cache coherence. I don't really tend to talk about coherence very much on the exams, just because we didn't do any assignments on it. So if you want to remember about cache coherence, then what I'd probably say is remember the issues that can come from it. False sharing, ping-ponging of cache lines back and forth. We have some techniques to mitigate the expense of that, but generally that's the kind of thing that you need to be aware of when you design a multi-threaded program that uses caching. You have to remember ping-ponging and false sharing as the fundamental issues. But generally I don't include any kind of multi-core caching stuff on the final. I hope to one day, because it's a really interesting problem too. Okay, hardware cache terminology. Okay, so this is a good thing to review. Blocks of data. That's actually incorrect, right? 32-byte blocks. Isn't it 64? Pretty sure it's 64. Anyway, well, you guys can look that up. But I'm pretty sure that's incorrect. So maybe I should go change that later. But anyway, the cache needs to keep track of various details. So we have things like, is there actually a line? Is there a block cached in this line? Is it dirty? Have I modified it? And a few other details as well. So we have these additional bits. And remember, the tag is very important to tell where did the block actually come from. And the cache has to rely on this so that it can write it back later as well. Okay, so the cache gets an address, and it has to figure out the various details from it. Okay, so the topmost bits are used as the tag. Now, I don't really go into all the other details of this in this slide, but you can go back and look at the lecture and figure it out. So we have very strict placement policies, and this is where cache sets come into the picture. So we'll say, hey, there's S cache sets, and we figure out which cache set in that collection of cache sets it is from some bits in the address that comes in. So like I say, every block from level K+1, or the level below the cache, maps to exactly one cache set. This is not configurable. It's hard-coded into the hardware. But within that cache set, it can fall anywhere in the set. So we have two extremes that come out of this. One where we have a whole bunch of cache sets, and each cache set has only one line, which makes it very simple to tell if its block is in there or not. So that's called a direct map cache. And then we also have one cache set with all the lines, and that's fully associative. Okay, so we have direct map at one end and fully associative at the other end. Okay, so this is the way we break down the address for that. So we have set index is really large because we have a very large number of sets, and then the bits above that are the tag, and that allows us to tell, is this a block in the set that we need, or is there a different block cached in the cache set that we need to evict? Okay, and then the block offset is just dictated by the size of the block in the cache. So this is the example here. Remember that direct map caches have a horrible problem, which is conflict misses. Because basically the cache can be really large, but if we have the just right access pattern, we may focus on a subset of the sets within the direct map cache, and we end up with a cache that looks smaller than it actually is. And conflict misses, unfortunately, are a pretty difficult problem to eliminate in software. Even if you happen to have really good locality and good stride, you can end up with big problems with your algorithm. And so conflict misses are difficult to resolve. Are there any questions about direct map caches? Okay. Fully associative caches, since we only have one cache set, remember we don't have any bits for the set index because we only have one set. So all of those bits are used for the tag. So again, if we have the same block size, the block offset would be the same as from before, but now our set index disappears and we have a large tag. And so now we use the tag to figure out which cache line it holds our block that we want, or if none of them have a matching tag, then it's not in here. We need to evict somebody and so forth. So it's easy to map to a cache set, but as far as looking for the block in the cache set, this is where it becomes a lot more complex because we basically have to do an n-way equality check to see which line actually holds our tag, our block that we're looking for. Okay, questions about fully associative caches? These are extremely uncommon in hardware, but they're extremely common in software. Okay, I don't know if anybody in my experience here, I've ever come across anybody who's implemented a non-fully associative cache in software for a real program that needed to do caching. It's like you almost always do fully associative caches. Okay, since we have these two things, we can blend them together, and so set associative caches are extremely common, so make sure you're very familiar with set associative caches. We have these two extremes, and we like to combine the strengths of each. So we have more than one cache set, and we have more than one line per cache set. And so notice here we have E lines and S sets. Okay, we already talked about this before. So you have multiple designs, you blend them together to end up with a general purpose solution that can handle these various extremes. Okay, so here's an example, and this is sort of the point that I want to bring out here. When we say E-way set associative, I got this question a lot on assignment 5, which kind of bothered me, because I'd say, hey, it's an N-way, let's say it's 4-way set associative cache with 16 cache sets and blocks are 64 bytes or something. And people would say, how big is that? Well, that's all the information you need. You can figure it out. Okay? When we say E-way set associative, E is how many lines per set. Then we'll say there's S sets, and the block size is B. And you can go figure it out yourself. You can figure out how large that cache is. Okay? So in this case, for example, we have 2-way set associative cache. Notice 2-way does not tell us how many sets. It tells us how many lines per set. So we take the number of cache sets. We can do like log base 2 on that, and that'll tell us how many bits we need for the set index. The remaining upper bits are for the tag, and obviously the block offset is still present, based on the block size. Okay? And so, yeah, we use the set index to find the cache set, and then we only have to check a small number of lines, so our logic is simpler because we're keeping our cache sets a little bit small. And this really helps reduce the potential for conflict misses. And this is the one thing that I'm sad about that we don't have anymore in assignment 5 is you don't get to see how serious conflict misses can still be with set associative caches. If you access memory just right, you can still end up with a huge number of conflict misses. But it's a lot less frequent than direct map caches. So just be aware of that. Any questions? Okie dokie. So caches, very important. It's funny because like the first half of the class, we talk about all kinds of crazy topics, but it kind of all gets back to CDECL. And in the last half of the class, we talk about all kinds of crazy topics, but it really gets back to caching and virtualization. Those are sort of the two fundamental themes of the last half of the term. Okay, line replacement policy, we have to figure out what to evict. The many, many different policies. Sometimes I like to include problems on the final exam like, hey, here's a policy. Tell me what you think of it. Is it good? Does it suck? So just be aware of that kind of thing. Typically, we look at LRU. Least recently used. We use this as a benchmark because it's easy to understand. You evict the thing that was accessed furthest in the past. There's actually better policies than LRU, but they tend to be too complicated to talk about, although I'm thinking about maybe next year on Assignment 8 making people implement one of those. There's a couple like ARC, Adaptive Replacement Cache, which can blend between LRU and LFU and actually achieve better hit rates than LRU, which is really good. But LRU is sort of the inverse of the clairvoyant policy where you say, I'm always going to evict the thing that I use furthest in the future. Because obviously, if you're evicting things with knowledge of the future, you're clairvoyant. And so it's sort of that is the best case replacement policy, but it's obviously impractical to implement. So LRU is an approximation of that. And so make sure you understand what LRU means because generally we compare stuff to it. Okay, let's see. Yeah, so hardware caches tend to use very simple policies. The kinds of policies that you see on CS24 finals are actually more along the lines of what you might see in hardware caches. Okay, let's see. Any questions about? Yes? Where's the information about when something was accessed, stored? Typically, that would also be crammed in the cache lines. Yeah. The cache lines are basically the repository of information for all of these details for hardware caches. Now, if we're talking about virtual memory, which, again, as someone pointed out in the feedback for Homework 8, are basically caches that would go into your page tables. Okay? So the page table entries is where clever MMUs would store that information. But it turns out that most MMUs are not terribly clever, and so all we really have are the accessed and dirty bits, and it's exactly like Assignment 8, where we have some kind of timer tick, and you use the accessed and dirty bits to go update other information. So sometimes the OS will keep parallel information. In our hardware caches, it tends to all be crammed in the cache line. Okay? Any other questions about that? Alrighty. Let's see. Yeah, so different policies for handling writes. And again, what I'll basically do is say, hey, it's write through, or hey, it's write back. I'm not going to really say anything else than that. Write through is slow because we basically don't cache up writes. We always write through. Okay. And remember that we also have write allocate and no write allocate. And I don't think I really mentioned those. But write allocate means if I have a write to an address I haven't yet read, so it's not in the cache yet, I load the line in, and then I do the write against the cache. But if it's no write allocate, if that line isn't in there, then I just do the write against memory. Okay. Obviously, what's best is write back and write allocate. The combination of those two tends to be what processors use because it's just the fastest. Okay? So you can see that write through, you don't really need to have a dirty bit. But write back you do, because you need to keep track of the fact that that cache line has unsaved information in it. Okay? Let's see, performance analysis. I tend to eschew this now. I used to get into detailed performance analysis of caches, but it is so hard to do this effectively, especially when you have multiple layers of caching, and it's a guess anyway. The only way you can really know for sure is to run your program on a processor and measure it. So I guess I'll go ahead and throw this stuff up here. So typically we talk about miss rates, the number of misses over the total number of references. Obviously that's a number between 0 and 1. We want our miss rate to be as low as possible. Hit rate is 1 minus the miss rate. And really like 0.95 and above is what we really strive for. 0.98, 0.99, that's what we really want to see if you're going to have a really good cache-friendly algorithm. Okay, but I'm not going to go into it in any more detail than this because it just sort of like I said, it's all so approximate when we try to analyze this stuff. So hit time and miss penalty, this is just some number of clocks. It's useful to know generally how many clocks a hit will be and how many clocks a miss will be because at least that'll tell you how bad it is relatively when you have a miss or something like that. So remember, L1 tends to be 3-ish clocks out, so it'll be anywhere from 3 to like maybe 8 clocks. L2 will be anywhere from 10 to 20 clocks, 10 to 30 clocks. And then L3, if you have it, might be anywhere from 15 to 40, and then anything above that. You know, like they say anywhere from like 50 to 200 is going to be main memory. But again, that's just sort of like not terribly critical. Okay, so I'll just throw this up here. You can see that the higher the hit rate goes, the closer you get to your main memory, your cache performance, not your main memory performance. And you get a huge benefit from getting up into the 95+% range. And so typically, if it's below 95, you don't consider it a very good, very cache-friendly algorithm. Okay, there are some algorithms that are just not able to be made cache-friendly very well. You all kind of saw that with the tree data structure in Assignment 5. Sorting is pretty terrible when it comes to cache utilization. It's because you're hopping around data a lot. You're comparing a lot of different things, and it becomes difficult to engineer that in a way that's cache-friendly. Any questions? Yes.
Because of that, why doesn't merge sort perform better than quick sort?
Why doesn't merge sort perform better than quick sort? Well, you can design merge sort to perform better than quick sort if you do it in place. Quick sort is just kind of like a naughty sorting algorithm just because it has the, what do you call it? There's like a special name for it. I can't remember. These cases where it performs as n squared instead of n log n. I can't remember. Is it like if it's almost sorted? Is that it?
Yeah, if it starts off sorted and you use the first pivot, then you get really bad performance.
Yeah, and also if you have a large number of, I don't remember exactly the way to say this, but if you have a large number of things to sort and they all are like, there's very few distinct values, you also get into the worst case behavior with quick sort. So there's other sorting algorithms, like there's one called Tim sort, which is really awesome because it basically tries to find runs in your data and then merges those runs. So it's very, very efficient. I think it can approach, again, correct me if I'm wrong, but I think it can approach order n for almost sorted data. Is that right? I believe it could get really close. So Tim sort is like my hero right now. I think there's other ones that are similar to that kind of algorithm. But with some of those, you can get closer to like a really cache-friendly algorithm, definitely. I just took my ring off. Why did I do that? It's just fun to play with. So I guess I have a fixation. So, all right. Any other questions? This stuff is really fun to talk about. I don't want to go into too much detail, obviously, for the sake of time. But creating cache-friendly data structures and cache-friendly algorithms is really interesting, and it's amazing how much of an impact it can have on your programs. And like I was saying, I've said this before, and now you all have the context to understand it, of course, that Python's dictionary implementation in CPython is very highly tuned to cache utilization, which is good, right? Because if you make dictionary fast, then everybody's programs are fast. If dictionary sucked and used buckets of, overflow buckets or something like that, you can imagine everybody's Python programs would really suck. Okay, so cache utilization is extremely important, and unfortunately, it's kind of becoming a lost art as people stay in these higher level languages more and more. Okay, so enough of that. The other thing that we talk about a lot is virtualization, which is just this notion that we can virtualize the processor in memory, and the computer that our program sees is different than the actual computer that is running the program, okay? Because we have all these virtualization capabilities. And I can't tell you enough how true this is becoming, even to the point that, like, I don't know, I probably don't have a guest operating system running right now on my computer. I can't remember if I shut it down or not. But a lot of you through the term have been using the CS24 VM. You're running a guest OS, and current processor hardware allows you to virtualize even that memory mapping stuff. Like, you remember we talked about the MMU and stuff. Can you imagine having a guest OS that expects to do page tables and rely on hardware memory mapping, and it has to emulate all that stuff in the virtual machine software? That's crazy. And so a lot of processors are now providing the capability of doing virtualization even of the virtual memory system, so that you can have multiple virtual memory systems, and then the host OS can allow those things to be exposed and make it very efficient. So this virtualization thing is so central to the way that we use computer systems, and it's going to become more and more that way. It's absolutely ubiquitous, and is only going to become more important. So we virtualize the processor, virtualize main memory. CS24, we have a very basic approach. We just talk about those things. Okay, so that virtual processor thing and the program running on it is called a process. So the easy way to think of it, I have a program plus its execution context. That's all a process is. Okay? And so obviously we have a lot of state that we have to manage there, and so that's what the operating system is responsible for. And of course, per processor or per core that we have, that thing can only run one program at a time. And so we have to basically time switch the processor between various programs. And so we have this notion of concurrent execution. And all that means is that we have overlapping logical control flows across multiple programs. Okay? Remember, Big difference between concurrency and parallelism. Parallelism is I do multiple things at the same time. I have multiple cores. Concurrency I can achieve on a single core by just having overlapping logical flows. Okay, so yeah, the process is running, and remember we have all of the support. We have to have a hardware timer interrupt to kick the process off if we want to do preemptive multitasking. The kernel should be the only thing that's allowed to manipulate that timer and so forth. So we have a lot of these details. Okay. I know I'm kind of going through this a little bit helter-skelter, but we'll try to draw it all together. We had a whole term to make sense, right? And now we're just sort of rapid-fire trying to cover everything. So this is the context on IA32. Again, you saw this in assignment 6 and 7, although we really didn't get into the management of the memory context because we didn't have virtual memory yet. Okay, so we started, yes?
When we don't do anything directly with EIP, correct?
You don't do anything directly with EIP. Well, yes and no. It's really wild because remember that when you call something, EIP gets stored on the stack. And we kind of relied on that, right? So we called into the scheduler, and you might have noticed that if you happen to look at how assignment 7 worked, when it's like the timer interrupt goes off, and it does this wild thing of getting the machine context for the interrupted program. I show you how that works in 124. It's totally badass. And in that machine context is the EIP of the program, because it's interrupted by the kernel. And you can actually manipulate the EIP directly because it's stored on the stack. And when you restore that context by doing a ret or an iret or whatever, then that gets loaded back in. So you can manipulate EIP, but not as directly as these other things. The other detail, of course, is when you have either a hardware or a software interrupt, the address of the next instruction is saved on the stack, and that's how we're able to access that stuff as well. So that's a sketch of the solution, but we really go through it in detail in 124. The same kind of thing with the flags also. Remember that the flags register is also stored on the stack by an int operation, so we can access those things in the machine context in the kernel or in a signal handler, but we don't really retrieve them and store them in the same way that you do the other general purpose registers. Okay. You guys are going to distract me with all these fun details. Anyway, so let's see. Switching between processes. So remember, this is a context switch. We have to stop the current process. We have to generate an exception or hardware interrupt to interrupt that process. We have to save various details. Remember, we transfer into kernel mode, and we may have to transition stacks. In fact, we almost always do. We have to switch contexts out, and then we have to undo all of that. So you can see that it's a little bit expensive. Again, if you want a ballpark, 20,000 clocks is a decent guesstimate for how expensive a context switch is. Yeah, I think I had a slide, a slide that goes through this stuff, so you can look in the index for that stuff. So there's two ways to drive this. One is through cooperative multitasking, which is what many operating systems that are not Unix used all the way up until relatively recently, which is kind of surprising. But that would lead to system hangs because you have one process that decides, for whatever reason, to go into a way that it can't ever yield the CPU, then the system hangs. And so preemptive multitasking is much preferred because you can interrupt somebody and kick them off the processor, and that way even badly behaving processes don't stop the system from running properly. Now, even though we have cooperative multitasking, I know I said this before, even though you have cooperative multitasking, it does not mean that the process has to explicitly yield all the time. All it really has to do is do long-running I/O operations, and that will implicitly yield the processor to other processes. So that's why Windows 3.1 could get away with cooperative multitasking, and Mac OS 9 and all the operating systems, Apple operating system for OS 10. Any long-running operation is a chance for the process to yield the processor, and the OSs would exploit that. Okay? But they could also manually yield if they were doing some compute-intensive thing. Okay, questions about that? Stuff is important. Let's see. So yeah, we do have hardware support for these different operating modes, kernel mode and user mode. Remember, kernel mode, you can do anything. Why do we call it a kernel? Because it's the part of the operating system that runs in kernel mode. That's really the only reason we call it the kernel. Okay. User mode is basically anything else. Can you have operating system code that's in user mode? Yes, it's a really good idea. We also have applications that live in user mode. Do we ever have applications that live in kernel mode? Yeah, not if you want a reliable operating system. Okay, so that's that. IA32 has 4 different operating modes. We're not going to talk too much about this because I cannot recall a CS24 final that actually relies on knowing that there's 4 different operating modes. Level 3 is user. Level 0 is kernel. That's really kind of all we care about. And it's expensive to jump between the two. Not as expensive as a context switch. We're probably talking tens to hundreds of clocks if I remember correctly. But it's kind of a small fraction of the context switch. It's still not free. That's the important details. It's still not free. Okay, let's see. Yeah, we need to be able to interrupt normal program flow for various reasons. Particularly if a piece of hardware says, hey, I've got your data for you, and it was taking millions of clocks to do it. So remember we have interrupts, which are kind of hardware exceptions, and exceptions, which are software generated. Okay. So traps, for example, fall under the exceptions, and faults as well can fall under exceptions. Okay, so interrupts caused by hardware. So this tends to be from peripherals or the advanced programmable interrupt controller on IA32, which is where the timers reside. Okay? So you can configure them to go off. Traps, intentional exceptions caused by programs. This is how you get into the operating system. Okay, so you execute some kind of trap. There's been various ways that we've done it in the past historically. Right now we use the int instruction, and it's a very straightforward operation. It used to be that there are all kinds of weird systems that have been created in wild ways in which programs would enter into the kernel. But right now it's very clean and straightforward. Okay, yeah, so the caller specifies the operation they want to perform in a register. Typically, arguments also have to go in registers. The processor executes the trap instruction and gets into the kernel, and the kernel is now responsible for making sure the user program didn't ask anything stupid or illegal or trying to get the kernel to do something stupid or illegal. Okay, and then once the operating system is done, then it goes back to the program with the answer, typically in EAX for IA32. Okay, so that's traps. Faults, unintentional exceptions caused by software. So these are maybe recoverable. So there's this one. It's really funny because somebody said, you know, what's a great interview question to ask a systems guy? And one of the questions that was posited was, what happens when you type ls enter at the command line? And you could go into that problem in such detail, and you can imagine all of these things that happen. You know, there'd be faults triggering and things like that being resolved by the computer system and so forth. So, but anyway, that's an aside. But you have maybe recoverable error conditions, and virtual memory paging is the most common example of this. So we try to access a page that's not in physical memory. It generates a page fault, which now has to be resolved. Or copy on write is another great example. The page is in memory, but somebody tried to do a write on it. So we get a general protection fault, not a page fault. And the operating system goes in and secretly does a copy of the page, changes the page table mapping, and now the process can write to that page all at once because it's private. Okay. So we have these various things that can be done to resolve. Now, fault handlers, just because it's a fault doesn't mean it is always recoverable. So if you have a situation where it's not recoverable, you typically send a signal to the process, and the default behavior of that signal is typically to destroy the process. Okay? So sig-seg-v, for example, the default behavior is to terminate the process. We abused the crap out of that in assignment 8. Okay? So, yeah. Did anybody have any weird seg faults that were difficult to debug in assignment 8 yet? Yeah, I had one. I mean, I'll admit it. I had one that took me like a day to track down. It was frustrating. But you learn a lot about debugging signal handlers, don't you? Because it's like, hey, look, there's kernel calls on the stack here. This is really wild. So you have some fun stuff like that. Okay, let's see. Aborts, unrecoverable fatal errors. So machine check would be an example of an abort. We basically don't talk very much about this, though. Okay, let's see. Exceptions. You know what? I'm going to have to pick this up because we only have 10 minutes and we have actually quite a few more slides to go through. We won't go through this. You can read about all of this kind of stuff. But int is the one that you use to invoke a software exception. Let's see, system calls. Yeah, so context switches, I talked about this, so you can review this stuff. Any long-running system call is a perfect opportunity for the kernel to transition away. We actually go through a lot of this in 124, where we develop the current operating system model that we have from what's come before us, so that's kind of neat. Direct memory access, we don't talk about too much on final exam, so you can review it if you want, but it is very, very important. So processor sets up a transfer from a peripheral to memory. The peripheral goes ahead and takes care of it, and then interrupts the kernel, interrupts the processor when the transfer is done, which can then be handled by the kernel. Okay, so that's DMA transfers, and this is exceedingly important for achieving performance systems now. Okay, but yeah, like I said, I don't think I ever really talk about this on final exam, so it's not super critical. Okay, so we'll skip over that. Signals are important. Remember, this is just a way of exposing hardware exception handling and software exception handling into the user process model that is in Unix. And this is very, very common across many different operating system types. I mean, Windows has this kind of thing as well. And so we have hardware exceptions that are mapped into signals, and also signals that can be sent between processes. Okay. Now, signal handlers are tricky. We need to make sure that they only contain reentrant code, because a signal handler can interrupt anything. So we can't call malloc in there unless we really want our program to crash and burn. We can't call some certain other functions as well. I do often include signal programs on the final exam, and they tend not to be terribly complex. So don't worry about, is it going to be the level of complexity of assignment 7 or 8? Almost never. Are the handlers reentrant? Probably not. We don't care. It's just to see if you understand sort of process life cycles and signal handling and so forth. Okay? So if you find that I give you a signal handling problem and you find a way in which the problem is completely broken, those typically make all the TAs and I chuckle, because it does happen from time to time. I think it was either last year or the year before, so I gave a problem and somebody said, well, this is what would normally happen, but in this special case it would actually completely fail. And I was like, yeah, that's very clever. That's actually accurate. Okay, so anyway, be generally familiar with processes and signals. So you have process IDs. You can start a process by calling fork. Remember, you call it once and it returns twice. Once in the parent. The parent gets the child's process ID because that is the only way that the parent can get that child's process ID. There's no way to enumerate a process's children. So fork returns the process ID of the child. In the child, the fork call returns 0 because the child process can just say, hey, what's my PID? And it can also say, hey, what's my parent PID? So there's no reason for fork to return a non-zero value in the child. So we can terminate by calling exit. And kill is the weirdly named function for sending signals to other processes. And kill does not automatically mean that it will terminate the receiving process, although that is often the default. So just be aware of that. Let's see. Also, when processes terminate, they become zombies. They don't go away right away, so they have to be reaped using either wait or wait PID. And you can use wait PID to wait for a specific child or for any of your children, which I think is if you put in 0. And if you put in like a negative process ID, it'll treat it as a process group ID. So wait PID is a very general purpose operation. Wait is more specialized. I just want to wait for any of my children to terminate, and it will block until that happens. It return the process ID of the child, and the out parameter here will be set to the termination status of the child. Okay, yeah, so unreap zombies. If you don't, the operating system has a mechanism built in. Like I said, it's the orphanage. So you terminate and you left zombies around. The zombies become the children of init, and then they get reclaimed. Okay, let's see. So execve is used to load and run a program. Remember, this heavily relies on virtual memory mapping. I don't really want to spend too much time talking about this, but yeah, on success, execve does not return because the context has been completely replaced by the new program. So if execve comes back, it's because there was a problem. Couldn't find the file, or the permissions weren't correct. Those are the two primary failure modes for execve. Let's see, any questions about these? All right, let's see, process control block, so that has all the details in it. This has different names in different operating systems. Linux calls them task structs, and task structs represent a thread in a process, not just a process. So you have these kinds of things. But this is where all the information is stored that the operating system keeps. And this was the general state model that processes follow. Okay? You should understand, like, why would I move between these different states? Remember, I can only make progress when I'm in the running state. It means I have a processor. If I'm not in the running state, then I'm in the ready state. If I'm waiting for the processor to become available. So that scheduling thing sort of happens in the top left. If I do something that requires a slow resource, I transition into blocked. When it becomes available, I go back into ready, and so forth. So you have this various stages that you move between based on these things. Why do we have suspended? Just because sometimes we don't want to schedule a process, even if it could run. Okay? And just so you know, process suspension is actually, it played far more prominently in the past when we had medium-term and long-term process scheduling. But right now we just do short-term process scheduling, and we rely on the user to say, oh, I've got too much crap running, I need to shut some stuff down because the system is not behaving well. Okay, so we'll talk about that in the OS class. Let's see, so the kernel has to decide what to run next, and so we have these requirements of schedulers. They should be fair. If it's going to be a general purpose scheduler, it needs to be fair. So we need to make sure every process gets at least a little bit of time on the processor every once in a while. It should be bounded. That's really what this term fair means. We also need to make sure that we maintain interactivity and so forth. So those are some of the requirements here. Okay, so we had round robin. Remember, round robin is everybody gets a time slice. You don't get interrupted while you're on the processor unless you decide to do something slow and then you yield. Okay, so this is good for compute intensive, but it's terrible for interactive. Shortest job first is great for interactive because you can sort of estimate how long the process's execution will take based on previous behaviors. You're estimating that burst length, the CPU burst length. And so interactive processes love this, but it can be unfair if you don't correctly manage processes that are in the ready queue for a long time. So you have to be very careful about that. And then earliest deadline first is what we frequently use for, I shouldn't say we frequently use it because it actually has a problem. But anyway, it is a simple scheduling algorithm that you can use for real-time scheduling. Okay? Just pick whatever's closest to missing its deadline. Okay, so multi-level feedback queues was the way that we blend all of these things, where each queue has its own time slice associated with it, and you move processes between queues. So that's basically all that we have here. The neat thing about this, of course, is that you can set aside some queues for real-time scheduling. They can be higher priority than everything else. And just by virtue of moving processes between queues based on whether or not they get preempted or whether they yield and are staying within their time slice, you categorize processes very quickly based on their behaviors. So this is why multi-level feedback queues are used quite widely in operating system implementation. Any questions about scheduling algorithms? All right, they're pretty important. I typically will have some process scheduling stuff. The main thing to be aware of is why we do these things and notions of fairness, and also interactive processes need to be higher priority and compute-intensive processes can be lower priority. Those are kind of the big things to keep in your head when you look at the design problems that pertain to scheduling. Okay, virtual memory. We're not going to talk very much about this because we already did. Let me see, address translation. We have this page table thing that we use to look up, and remember now context switches are fast because we just switched the page table. But even fast context switches are still 20,000-ish clocks. And remember that switching your page table has a huge negative impact on caching because I basically have to throw away the contents of my hardware caches because I just changed what's actually mapped to various addresses. Okay, so you can see that there's costs associated with context switches. I just want to make sure everybody understands they're not free. Okay, translation look-aside buffers, very important, so that we can actually make this address translation fast. Okay, there's many other techniques that are used, but obviously we've only kind of scratched the surface on this stuff. Let me see what else. So multi-level page tables, make sure you understand the reasons for those. We kind of only talk about these in class. The first time you'll really have to manipulate these is if you take the OS class. Then you'll have to manipulate page directories and page tables. Okay, remember page table entries? I would definitely recommend going through that stuff and understanding page table entries and just like what kinds of bits. You have permission bits. Is it present in memory? Is it been accessed? Is it dirty? Because those are kind of the most important details to be aware of with page table entries. And then, like I kept harping on when we talked about virtual memory, the virtual memory system is the #1 place where the OS and the hardware have to interface because there's a lot of stuff the hardware does if it possibly can. The memory management unit will do all the address translation it can just based on the configuration of the page table. But if it can't, it faults into the kernel. And then the kernel has to deal with manipulating the page tables, the supplemental page tables or VM area structs, those kinds of stuff. And so the OS and the hardware work most closely, most collaboratively when in the virtual memory system. Okay? Any questions about that? I know we just spent like 2 weeks talking about it, so that's why I'm not going to spend very much time about it. Okay, let's see. In fact, I'm going to go ahead and skip over all of this stuff. Faults for 2 main reasons. Page isn't present or access isn't allowed. You already got to see that in assignment 8, so we won't spend very much time talking about that. And we also talked about this. Okay, so let's go ahead and wrap up CS24, at least like I said, the official part, because Friday we will have a for fun lecture on some topic. But I wanted to make sure to go over the final themes of CS24 just so that we put the appropriate capstone on it. So we have common case optimization. Make the common case fast, make the fast case common. Okay? You saw this in hardware, how we try to make the common case fast. And then in software, if we have a common case that's fast, let's try to work, use the crap out of it. And so we do this address alignment stuff. We try to lay out memory data structures so that they leverage cache lines, and we try to utilize the file system in a way that's efficient and so forth. So we basically try to leverage this optimization approach as much as possible. Then we have hybrid solutions. We have multiple techniques with special strengths, and so we try to come up with general purpose solutions that combine these various specialized techniques. Remember, we saw that with garbage collection, set associative caches, multi-level feedback queues. Those are 3 very obvious examples where we build these hybrid solutions. And then virtualization, which, like I said, is like super important for having hardware that we can share amongst processes and even now operating systems, which kind of blows my mind because that was not really a thing we considered back when I was an undergrad. Okay, so yeah, we have the OS mediating access to the hardware on behalf of applications and now on behalf of guest operating systems. Okay, I think that's it. Any questions? All right, well, good luck on the final. And like I said, we'll have a special fun lecture on Friday, which you are not required to attend. So maybe I'll see you.